Chapter 2, Derivatives, and 2.1 is the derivative function. So once we're in Chapter 2, we start finding derivatives using first principles, which is the difficult way to find a derivative. But once you've learned that, we move on to the basic rules for finding derivatives. It will take you probably 1/10 the amount of time required. But you have to understand where it's coming from, right? Just like everything else. It's kind of like a proof, and you will definitely be asked to find a derivative from first principles for something, either on a unit test or on a final exam. So you need to understand. So this is the whole derivative function that we talked about before. It's a slope function. Remember I told you that a derivative was basically a slope function. So f prime x is talking about the limit. It's a limit as h approaches 0, so we understand what limits are now, of f at x plus h minus f at x over h. And what we're going to do is I'm going to do the three basic calculations for a polynomial, a radical, and a rational function, and how you go about finding the derivative function. So the first one, f at x equals x squared. I'm going to write it out. First I write f prime x. So that's going to be equal to, now if you didn't have this written here already, I would suggest you write that out as your opening statement, and then you plug in your limit. The limit as h approaches 0. So f at x plus h, all I'm doing, remember in grade 11, all these things you had to do where you plugged in. So you have x plus h squared minus f at x is x squared over h. And as we discussed earlier, when you're doing these, well, in the previous chapter we did them, we'd say, what is the slope at 2? Well, instead of finding the slope at 2, we want to find what is the slope for any value of x. And that's why here we're just using f at x. So in order to complete this, I need to expand and simplify. And remember that somehow we're going to get rid of this x squared because everything in the top has to have an h, so I have something to divide this h out into in the numerator. Or else I'd have a 0 in the denominator, right? Okay, so I square, I twice the product, 2xh plus h squared minus x squared all over h. And you can see these, x squared minus x squared, everything else has an h. And that gives me the limit as h approaches 0 of h times h plus 2x. I'm going to write it like this, or it doesn't matter if you turn those the other way around, but I think you need to see, I would not write this step up normally like this. And now I plug in h is 0. When h is 0, I end up with 2x. And this, in its simplicity, is very complex because what it tells me is that if I had the graph of y equals x squared, and I'm going to draw it up here, hopefully it's still on the screen. If I have the graph y equals x squared, your super basic parabola, right? And I know that f prime of x is 2x. So that tells me when x was 0, so f prime at 0, now I can say, oh, the slope at 0 is 0. What is the slope at 5? The slope at 5 is going to be 10. What's the slope at negative 2? Oh, it's going to be negative 4. Watch, 1, 2, negative 4, 0, 5. Oh, I didn't draw it out far enough to show you, but it would be something like that, right? So this is a very powerful little function that now you can determine the slope for any value of x to the graph of x squared. Remarkable, isn't it? You should be impressed and wowed and thrilled. Okay, so let's look at what you would do with the root of x. So the same thing. I'm going to write out f prime x is equal to the limit. Don't forget your limit, and don't forget to keep it going all the way down until you plug in that value. So I want f at x plus h, so that's the square root of x plus h minus the square root of x. That's f at x over h. Now how do I simplify this one? We multiply by the conjugate. I heard you say it out loud. I'm glad you're following along. So I write this out, and whatever you do to a numerator, you must do the same to the denominator. And don't forget, forget that part, that we now have this times this in the denominator. You might want to put brackets around it if you need to. Okay, so I expand, and I have the limit of h approaches 0. So root x plus h times root x plus h is x plus h. We don't need to worry about the middle terms. And negative root x times positive root x is minus x. And look how lovely that is. So I have made a mistake. What did I do wrong? Nothing. I have x minus x. Oh, I forgot to write out this part. Here we have the root of x plus h plus root x. That's still all in the denominator. So the x's cancel out. The h divides into the h one time. I don't know, for some reason today I keep thinking every time I divide it out it's disappeared. But there's a 1 there. And so I have 1 over, and I have plug in my 0 here. So I have the root of x plus the root of x. What's root x plus root x? 2 root x's, right? Don't make that mistake. Some people sometimes multiply them and do something silly. So that means that if I wanted to find the slope, let's draw a little function here of the root of x. Oops, that's very crooked. So let's say I had the root of x here. Now I want to know, what is the slope when x is 4? So the slope when x is 4 is going to be 1/4. Oh, look at that. That looks like 1/4, doesn't it? Well, maybe not, but it is. So again, very powerful. Now let's take a look at this one. There's really 3, and then you might have, something added to it. It might be a little more complicated. But basically, if you can do these 3, you should be able to do any of the other ones. Okay, so I write f prime x. And remember that this first principle stuff only lasts a little bit longer. We're going to make it much easier in a minute. So the limit is h approaches 0. Okay, so these ones are the ones where you have, something over something. So be careful with your somethings over something. So I have this. So that's my f at x plus h minus f at x. Now you can write it over h. I said that before, but it just makes too many messes there, right? So I'm just going to write it over here, times 1 over h. That's the same thing. Okay, now in order for me to add these together, I need a common denominator. So what you should be remembering is plug it in for this one, multiply by the conjugate, find a common denominator. So I have x plus h times x. And in the top here, I would have x minus, and this is where most of the mistakes happen because it's minus, right? So it's minus x minus h when you multiply this by x plus h, right? Negative each of those. And this side times x. So I have x minus x, and the h divides into this h here. So x minus x, h goes into h minus 1 times. So now I have the limit as h approaches 0 of minus 1 over x plus h times x. I put in h is 0, and I have x times x, and I get minus 1 over x squared. Okay, so those are your derivatives from first principles. I'm going to show you something really, you're going to say, oh, why didn't we do this earlier? But if we have something like x squared, so if f at x equals x squared, for the derivative, all I have to do is bring the 2 to the front and reduce the exponent by 1. So if I have f at x equals x cubed, then f prime x is going to be, bring this to the front, reduce by 1, 3x squared. And you might say, well, what happens to this one, 1 over x? Well, you should know. I have room here. So f at x equals x to the negative 1, doesn't it? That's 1 over x. So f prime x is going to be, I bring the negative 1 in front, and I reduce this by 1, and that gives you your minus 1 over x squared. So as we go along, this is going to make more and more sense to you about how important these first principles are in order for you to do the more difficult questions easily. The last thing we're going to talk about in this section is what is a differentiable function. So a differentiable function is differentiable at a point if its derivative exists at that point. Basically, can you draw a single tangent at that point? So for instance, if we have the absolute value function at x equals 0, it is not differentiable. And the reason is, I'm not going to write that all out, I could draw a whole bunch of tangent lines here, right? At this point here, I could draw one like this, I could draw one like this, I could draw one like this. So there's an infinite number of points on that teetering point right here. It's like, you know, being at like this one here. How many can I draw? Well, I could draw one like this, I could draw one like this, and if you want, you could make a little kitty cat out of that and say, no, it's not differentiable. It's not differentiable at that point. At this point, well, obviously, the function has a jump discontinuity, and I can't draw a tangent there. And maybe more surprisingly is the root of x at x equals 0, because this is the tangent line here also cannot be drawn. Now, the final thing we're going to talk about is notation. We use the prime function, f prime of x. This is the most commonly used. And some textbooks, especially the older ones, it's faster too, right? They write dy dx. That means the derivative of y with respect to x. Math is very respectful. Or d dx, which also means the derivative with respect to x. Now, of course, if you had different variables, you'd change them here. So let's say I had an equation that was, I don't know, s squared, so d ds. Or that would be for a position function, right? Or ddt or ddv, or could be all sorts of different letters. But those would be the three different types, with credit to, I forget who did this one. I think it was like Galois or something, and Leibniz, and I don't know, they were all fighting over who had the best method. This one wins the prize for me because it's the most simple. And that's your lesson for today.